welcome viewers on the second lecture of NPTEL on calculus of variations. Let us recall what we did in the first lecture. In the first lecture, we got introduced to certain concepts on the calculus of variations. Here I mentioned these two books which will be followed as reference books, that the calculus of variations with application by Robert Weinstock. This is a Dover publication, appeared in 1974. The second book is a famous book by Elsgolz, Mir publications, 1970. The title of the book is Differential Equations and the Calculus of Variations. So, these two books will be covering the material for 20 lectures, which are going to be delivered by me on the calculus of variations. So, let us recall what we did in the first lecture. As mentioned, the study of the calculus of variations started by the problem posed by John Bernoulli. This is double N. John Bernoulli in 1696, which he proposed a problem known as Brachester-Cohen problem, where he asked to find a smooth curve in a vertical plane joining 2 points A and B not on the same vertical level, such that the time taken by a particle sliding under the influence of gravity takes the least time. In that year 1696, famous mathematicians like Newton, Lebanese, John Bernoulli and his brother Jacob Bernoulli, and many other like L'Hospital, all these people solved the problem in that very year. So, the interest got created on the study of calculus of variations, and many more problems were posed and solved using the techniques of the calculus of variations. We saw the second problem, where in a plane there are 2 points A and B. Then we asked to find a curve such that the length of the curve joining these 2 points is the minimum, and we know the answer is the straight line joining these 2 points A and B in a given plane. And we can see that it can be posed as a problem of calculus of variation, like the minimization of the functional L, which is a function of y given by integral x1 to x2 square root of 1 plus y prime square dx, which is nothing but the integral of the element length ds integrated over the interval x1 to x2. We will see that when the sufficient tools developed for this calculus of variations, we will see that the answer will be actually the straight line joining these 2 points. Then other problems like isoperimetric problems, where a curve is given in a plane where its length is fixed given by L, and it is asked to find a surface which is enclosed by this curve. So, this problem is also can be posed as a problem of calculus of variations. We will see that here in that case the answer will come out to be the flat surface enclosed by the curve whose length is fixed given by the length L. Now, this is the concept of the calculus of variations is similar. It is a generalization of the concept of finding the another problem of calculus of variations can be seen that given a curve C here whose length is L, which is a fixed number, and we are asked to find a surface enclosed by this curve C. Here this is an isoperimetric problem where the parameter is fixed, and you are asked to find a surface which is enclosed by this curve C whose length is fixed. So, in that case here it can also be seen that S surface area given by z of x y, where this surface will be given by z of x y is given by the double integral square root of 1 plus z x square plus z y square dx dy, and here length of this curve will be fixed, that is given by the earlier integral, which is parametrically we can see that the length of this will be given by x 1 to x 2 square root of 1 plus y prime square dx. So, such a thing is can be posed as the problem of calculus of variation, where you have one quantity which is to be optimized under the given condition, which is known as a side condition, like the length of the curve is fixed and we are asked to find the surface such that the area of the surface is the minimum or maximum. Here let us recall that certain concepts related to finding the points where a given function takes the minimum or maximum value. Here there are certain points where function takes the maximum value over the whole interval. Such a point is called global maximum, or at a certain point the function takes the minimum value over the whole interval, such a point is called the global minimum. And there are certain other points in the interior of the interval, or it may be at the endpoints also, where the function can have local minimum or local maximum. So, for example, at this point x 1, in the neighborhood of this there are points where the function is having larger value than the value at the point x 1. Similarly, at the point x 2, in the neighborhood of this there are points such that function f takes lower value than the value at the point x 2. So, these are the points where f takes local minimum and local maximum respectively. So, here when function has smooth properties like its derivative is continuous, then you can see that at the interior points, if the function takes local minimum or local maximum, then the derivative becomes 0, the tangent becomes horizontal at those points, whereas at the end points we may have to check the values of the function separately and compare it with other values, so that we can check whether at the end points global minimum or global maximum is occurring or not. And at other interior points, if function is smooth, then we just check for the equation f prime x equal to 0 and solve for those x such that the f prime takes value 0. So, at those points we will check then the whether these are the points candidates for minimal or local minimum or local maximum, and then we go for higher order derivatives, other tests to check whether we have minimum or maximum at those points. Then here we define the concept of functional. So, it is that in the case of a function, a function assigns a number in this interval a b to a number in the real line r, whereas in the functional case this functional L defines, it assigns a number to a given function in the class of admissible functions, like y belonging to a the admissible class over the interval a comma b. It assigns a number L y which is a real number, and it is given like in this example given by the integral x 1 to x 2 square root of 1 plus y prime square dx. So, given y, we have the length L as a real number, positive real number, non-negative real number here, such that it assigns to each curve smooth curve, so that y prime is piecewise continuous, so that this integral is well defined. So, this L will assign a number to such admissible curve. Here admissibility is that y prime should be piecewise continuous, so that this integral is defined in the sense of Riemann. And so, this functional L assigns a number L y to this function. Such a thing is called functional, and here we will have, when this integral or we have more general forms of integrals where y prime, y double prime appearing in the integrand, then we will take the higher order continuous spaces, which are spaces defined as C k, where k is a non-negative integer over the interval a b, endowed with the supremum norm over the interval a b. So, for example, in this case you have two curves y 1 and y 2, and L assigns a number L y 1 and L y 2 to each of these curves joining these 2 points a and b, and these are L y 1 and y 2 are from the class of admissible functions. They are such that y 1 prime and y 2 prime are piecewise continuous, so that the integral defining their lengths is well defined. So, then next we consider the general form of integral I, which may appear in our analysis, and the other higher order other integrals which will involve higher order derivatives will also appear in our analysis. For example, this I here is an integral defined over the interval x 1 to x 2 of a certain given function f, which has continuity property of that f is continuous of its arguments, and this y and y prime, y is continuous whereas y prime is piecewise continuous. So, then this integral will be well defined in the sense of Riemann, and here the boundaries, these points a and b are fixed here. So, each of the admissible function belonging to the admissible class must satisfy these boundary conditions that they are passing through these 2 points, and so the each of the admissible function should actually be in this class such a way that these boundary conditions are satisfied. Then we are supposed to find a y which will actually optimize the value of this integral, whether it will minimize or maximize. We will be actually saying that I gets optimized by the function y. And then other kinds of integrals, more general forms, like where you have several dependent variables y 1, y 2, y n appearing like this, the integral over x 1 to x 2 f of x is the independent variable, whereas y 1, y 2 are dependent variables, and their derivatives y 1 prime, y 2 prime and y n prime are appearing. So, here you would have these additional conditions, like these are to be satisfied, so that each of these y i's are passing through the points a and b, like you have y 1 at x 1 is y 1 0, y 2 at x 2, y 2 0. Similarly, this also be satisfied, and y n 1 and y n 2 at the point x 1 and x 2. So, these are the conditions to be satisfied by each of these y i's, and then we are supposed to find the interval y 1, y 2, y n such that this integral is optimized. Then there are other integrals in the form where, although the dependent variable is only one here, but then there are higher order derivatives appearing. So, integral of x 1 to x 2 f of x y, y prime, y double prime and so on up to y nth derivative, and y is from C n x, or piecewise you can say that the highest order derivative can also be allowed to have discontinuities of first kind on certain finitely many points inside the interval x 1 to x 2, and then these are the conditions on y up to n minus 1 derivatives, and so at each point x 1 to x n and x 2, these are the conditions to be satisfied by y, y prime and y up to y n minus 1. Then a more general problem would be where you have more independent variables appearing, like x 1, x 2, and then z is a function of x 1, x 2 surface such that here this is the derivatives with respect to x1 and x2 are piecewise continuous, then you can consider this integral of this f, which is a function, a continuous function of all of these arguments. Then the integral is again defined in the sense of Riemann here over the domain D, which is an open connected subset of R2 here. So, at each point x y there is a point x y z x y on the surface, and this integral I is a function of z. For when we change this z, this surface z, the value of I changes, and so we are asked to find a surface such that z such that this I is optimized. Such problems appear in connection with certain partial differential equations, and those partial differential equations can be posed as optimization problems, as problems of calculus of variations equivalently like this. That is what we will see subsequently in our discussion. Then certain preliminaries were discussed in the last lecture. We had certain function f from x1 to x2, and it is called continuous if the left and right limits exist, and various examples were discussed in connection to that. And then piecewise continuous functions where discontinuities of first kind are allowed, and only at finitely many points inside the interval, bounded interval x1 to x2. Then piecewise differentiable functions where function is continuous and this f prime can have the discontinuities of first kind. Here f prime is assumed not to change sign at infinitely many points inside the interval x1 x2, so as to avoid the case where the derivative f prime, left derivative and right derivatives are equal, but they are not equal to the value of the derivative at that point. Such situations will be avoided if we assume that f prime does not change sign at infinitely many points inside the interval. Then we consider partial and total differentiation of a function of several variables, where in the first case when function u is a function of n variables x1 x2 xn. So, it is a function from Rn to R such that the first order partial derivatives exist with respect to its variables, and then xi's are in turn functions of several variables t1, t2, tm. Then the partial derivative del u over del ti can be defined like this, and in particular if xi's are functions of only single variable, then this partial derivative with respect to t reduces to the ordinary derivative du by dt in the following manner. And then we consider the Lebanese rule, which states how one actually differentiates an integral where the limits are variable limits, and this integrand is function of several variables. One, like in this case f is function of two variables x and t, limits are functions of t, and the variable of integration is x. So, here I is treated as a function of t, and therefore, we can consider its differentiation with respect to t provided f has certain differentiability properties with respect to t. So, this can be defined like this: I prime t is f of when this t will be replaced by, actually it should have been x and x2 t like that, and dx2 over dt minus f of x1 t dx1 over dt, and then x1 to x2 del f over del t xt dx. That is what we will have here. Okay, so this is so the first term is f of x2 t comma t dx2 over dt minus f of x1 t comma t dx1 over dt. So, these differentiations of the limits is assumed here that they are x1 and x2 are differentiable functions of function t, and here inside this integral, the third term x1 to integral of x1 to x2 del f over del t of x t, here it is assumed that this f is the partial derivative of this f with respect to t exists, and it is piecewise continuous function. So that this integral is well defined. Now this was the proof of that. Now we start in this lecture on these remaining concepts which will be required subsequently in our analysis. Now the next one is integration by parts. It's a very useful formula which gives us integral of one thing where we have two functions appearing in terms of integrals of the same function in a different form. Like you have x1 to x2 f prime x g x dx. This can be seen that this is equal to minus integral x1 to x2 f x g prime x dx plus f x to g x evaluated at the boundary points x1 and x2. Here this so what it states that here you have two functions f and g, where f and g are assumed to be, so f and g are continuous and f prime and g prime, or f and g are piecewise differentiable on x1 to x2. So then these integrals will be well defined. Here this can be seen by the result that when you differentiate f into g, this is equal to f prime g plus f g prime. So integrating this on the interval x1 to x2, is equal to x1 to x2 f prime x gx dx plus till x1 to x2 f x g prime x dx. Now this is integration of differentiation of this term. So this will cancel and it will give you the values at the end points. So this side will be f x g x evaluated at x1 to x2. So that is equal to x1 to x2 f prime x g x dx plus x1 to x2 f x g prime x dx. So you can see that on the left side of this star, here we have x1 to x2 f prime x g x. So this is equal to the values of f x g x at endpoints x1 and x2. So that means this is actually f of x2 g of x2 minus f of x1 g of x1. That is what actually this side is equal to. So the f x g x evaluated at x1 x2 and then minus evaluated at x1. So this any of these terms can be seen that this term is this side minus the other term which is appearing here, the first term on the right hand side of star. So this is established using this fundamental concept that f into g prime is actually f prime g plus f g prime, and then integrate this identity over the interval x1 to x2. Next we have the Euler's theorem. on homogeneous functions. So, what it says that first the concept of homogeneous functions, a function f of several variables, like you have x1, x2 and xn, and then you have u1, u2 and um. So, this f is a homogeneous function of these variables u1, u2, um if it satisfies is homogeneous in u1, u2, um if f of x1, x2, xn, h of u1, u2, h of u1, h of u2, h of u3 and so on, h of um is actually equal to h to the power n. This n is called the degree of homogeneity of the function f, x1, x2, xn and u1, u2, um. So, this function f is homogeneous in these variables u1, u2, um if we have f of x1, x2, xn and h of u1, comma h of u2, comma h of u3 and so on up to h of um is actually equal to this h comes out with power n here. So, n is called the degree of homogeneity of f with respect to u1, u2, um. So, for such a function, Euler's theorem states that it says that del f, this summation u j del f over del u j, j going from 1 to m, this actually equal to n times f. This f is of course evaluated at x1, x2, xn and u1, u2, un. So, this is what is the Euler's theorem for homogeneous functions, which will be very useful in our discussion. Next concept is the concept of method of undetermined Lagrange's multiplier. Lagrange's method of undetermined multipliers. Here in this case, we have this function f of several variables x1, x2 and xn here, and we have certain conditions. Is a given function and we have conditions Gj of x1, x2, xn equal to 0, j is from 1, 2 to m. So, there are m conditions. So, these variables x1, x2, xn are supposed to satisfy these m conditions. Then here this then the necessary condition the necessary condition for f to have minimum or maximum at x1, x2, xn is that del over del xi of f plus summation j equal to 1 to m lambda j gj, this is equal to 0 at x1, x2, xn. Here these lambda 1 are, so the points, these lambda 1, lambda 2, lambda m are called Lagrange's multipliers. These are unknown and they are to be found in addition with the points of minimum or maxima. So, when we want to find the points of minimum or maxima of this function f, here where there are these m conditions given, these are to be satisfied by the point, those points where f attains minima or maxima. Then the necessary condition is that we should have these I equal to 1, 2 to n. These n conditions are to be satisfied at the point x1, x2, xn where this f attains minimum maximum. Here the points x1, x2, xn are to be found, and also these lambda 1, lambda 2, lambda m are to be found in this process. The next concept is the line integral. Here we have seen the integrals of this kind a to b f x dx. So, here this simple case where we have certain interval here x1 a b here on the x axis, and this function f is given over this interval, and we know in the sense of Riemann we can define this function a to b provided f is piecewise smooth function. So, the generalization of this, that you have in 3 dimension, let us say x, y and z, and here instead of this interval a b, here we have certain curve given here like this c, and this is a point a, this point b, like we move from a to b, we move from this capital A to capital B here. So, this defines the direction of the movement on the curve c. If we move from B to A, then that is the negative minus of the movement of what we do in the forward direction A to B. So, this clearly fixes the direction on the curve c here, and there is a function f x y z defined from any point x y z here into this gives you a value in R. So, we are supposed to find here we are supposed to define the notion of integral of this f over this curve c in certain sense here, and we will have certain, let us say, over the arc length. So, S denotes the arc length here, and this is a distance from any fixed point to a movable point here. So, let us say point A is fixed. So, the length S, the arc length S is the length of this curve along the see here, if P is here, now this S will denote the length of this arc up to A to P. So, as P moves along this, the S increases here. So, that is the arc length parameter, or in general we may take we may parameterize this curve like this. So, the curve C is parameterized as x t, y as y of t, and z as z of t. Here t ranges between A to B. Then here this curve C is assumed to be piecewise smooth, in the sense that these x, y, z are piecewise continuously differentiable. Their derivatives, see, x, y, t are continuous, and then their derivatives are piecewise they are piecewise continuous functions. So, x prime t, y prime t, z prime t are defined at all points except at finitely many points where they have jump discontinuities. So, this curve is called the directed curve, provided we have this kind of parametric representation here. Then if you partition this curve like this, that is like you partition the interval A equal to t0 less than t1 less than t2 and like this, and you have tn which is B, such that so this is the partition Pn, and the length of or the magnitude of the partition is defined like that: maximum of Tj minus 1, where j is from 1 to n. Then we consider this kind of sum Sn, summation j equal to 1 to n f of, here on the interval we have, let us say, xi j belonging to Tj minus 1 to Tj. Then you define f at x at xi j, y at xi j, z at xi j into Tj minus 1. Now, if this limit exists, if this limit as Pn tends to 0, as the size of this partition, which is the maximum of the largest length of the sum interval. So, if this tends to 0 and if this limit exists, as this mod Pn tends to 0, provided this limit exists, we define that to be, so the limit is defined as integral over C f of x, y, z dt. So, x, y, z are functions of t, and so this is defined in the sense of Riemann as in this case here. So, if this limit exists, then we say that this integral, line integral exists. So, in particular, if t equal to s, then if t equal to s, the arc length then we have integral over C f x y z, then x y z will be functions of s and we will have ds, and we can see that this is actually equal to integral over this f x. So, if we change the variable here, we will have x t then and some other. So, x y z, and ds can be seen dx by dt square plus dy by dt square plus dz by dt square dt. So, that is the from one variable to another, the arc from arc length to any general variable, we have this relation here. So, the line integral here for any curve, given piecewise smooth curve here, such that the function f is having the property that it is piecewise continuous on this, in the sense that on this interval the function, this f of f x t y t z t, this defined as g t. So, this will be a function of t only if this is piecewise continuous on the interval a b, and if the curve is piecewise smooth, you can see that this integral is well defined in the sense of Riemann. So, here any general parameter t is there. If parameter t is replaced by the arc length s, we have this form of the integral. There are other forms of line integral like f x y z dx over c, or f x y z dy over c, f x y z dz. So, these are actually particular cases of this, because this can be written like this f x y z dx can be written f x y z dx by dt dt. So, or in particular we can take s here. So, if we treat the parameter as the arc length, then we have everything as a function of s. If we treat if we take the general parametric representation where parameter is t, then we can have this. So, these are nothing but they are particular cases here. So, this f is actually replaced by f x y t dx by dt here, which is of the form we have this kind of general form of line integral. So, these are all can be treated as particular case of double star given here. In general, we have this form of line integral where we have f1 x y z dx plus f2 x y z dy plus f3 x y z dz. So, this can also be, because each one can be defined like this, and so each of these integrals are nothing but the sum of their respective, here f is replaced by those f i's here, and so this general form can be treated in the same manner. This is actually the vector form of this is the following. You have f f r like this dot dr, where f is the vector f is f1 x y z I, f2 x y z j plus f3 x y z k. I, j, k are the unit vectors along the coordinate axis. This is x, this is I, j, k. So, this f is in general this vector function of x y z given like this, and our position vector r for any point p here, this O p. So, this is x y z. So, our position vector r is given by, which is nothing but directed vector like this O p x I plus y j plus z k. So, dr element will be dx I plus dy j plus dz k. Now, if x, y, z are parameterized by parameter tree along, so that the point x y z is lying on a curve, then this r will be a function of t, and so we can have dr over dt will be dx over dt I dy over dt. If p is on C, that means p is x t, y t, z t, this point, or this is the another notation can be x t I plus y t j plus z t k. Then we can see that this dr by dt, the tangent vector at the point P on the curve, will be given by dx by dt I plus dy by dt j plus dz by dt k. And so this f r dot dr, this integral over C will be nothing but f 1 dx plus f 2 dy, sorry, this little f 2 dy plus f 3 dz. So that is what is the line integral which we considered here. So that it is actually the vector form of the line integral written in this manner, which is same as our line integral, the general form of the line integral. Now here one particular case of this which we will be using the following, that is two dimensional case where I is taken as half of integral over C. So here this is a plane curve in x y, like this, and then this area, this domain D is enclosed by this C. This is the curve C is taken in the positive direction, is taken counterclockwise, and so when it is closed we write the circle here and half of this x dy minus y dx. So this is a line integral which is of the form this one, where f 1 is, so in this case what f 1 is minus y and f 2 is x and f 3 is 0, y by 2 rather, x by 2 and f 3 is 0. So we can see that this I is a particular case of this here. Now this actually gives the area of the domain D enclosed by this curve C, which can be seen using the Green's theorem. So Green's theorem says that if you have any plane curve like this, and this is the region enclosed here, see here we will take a very special case where any vertical line like this, it cuts at most 2 points, like here it cuts only at one point, or here it cuts at one point, and at other points this vertical line and similarly the horizontal line, the lines parallel to axis cut the area D at most at 2 points, or situation may be like this also, the whole segment can also come like this vertical line here, if you this D is there. So and C is the curve enclosing this D, this vertical line here should take then the whole segment as common points with the domain here. So we can allow this also. So in particular, first we will take this the simplest case where we have this case that the vertical line takes only at most 2 points common with the domain D and D closure. So the D is domain, so the D closure is actually D union the boundary of D. So, only 2 points here, this and this will be having intersection with this vertical line with this D closure here. So, for such simple areas we can state the Green's theorem and then extend it to this and more general areas like this. So, Green's theorem says that the integral over this C m dx plus n dy is actually equal to this double integral nx minus m nx minus my dx dy. Here it is assumed that the partial derivatives of n and m are continuous in this region. So, that this integral will be well defined here, and on the boundary m and n are continuous. So, on D the partial derivatives exist and they are continuous in D, and m and n are on the boundary they are continuous. So, that this integral line integral is defined, or you can allow them to have piecewise continuity also. So, that the integral has to be well defined. So, this is what is the statement of Green's theorem under these restrictions on n and m, that m and n are here inside D the partial derivative exists and they are continuous, and on the boundary that means on C m and n are piecewise continuous. So, that is what is required, and under these conditions we have integral line integral m dx plus n dy equal to double integral over this domain D of nx minus my dx dy. This can be seen easily, like in this simple case first we prove it for this. So, let us say this is A here and this B here, this is the x range like this, maximum range here, and this is A is minimum of this. So, x range, then we can define this, let us say this curve as y1 x from here to here going like this, and y2 x like this, y2 x. Then the integral this minus my dx dy can be written as the iterated integral a to b and y1 x to y2 x of m x y y partial derivative of m and dx, first dy and then dx. So, here when you this differentiation integration will cancel each other and will give the values at the endpoints. M x y1 x or y2 x minus m x y1 x dx. Now, here we can see that minus sign is there, and along this m is integrated along this curve y2 it is integrated. So, and because of this minus sign we will have this direction gets reversed, and similarly in the second term here along this y1 we will have, so this minus minus will make it plus, and so therefore, this will be the direction taken from A to B. So, this is actually nothing but the integral of this m x y dx, because in the first term we have minus here. So, we direction gets reversed. So, it goes from B to A. So, this is actually equal to from B to A if you adjust this minus sign. So, it is like this B to A m dx or m x y to x dx, and then plus a to b m x y1 x dx. And so, the first term is going from b to a for the upper one, and so it gives you this part minus of y2, and so overall this is the direction we have taken. So, this is the integral line integral m x y dx on the closed curve C. Similarly, for this n x we can do the calculation here, which will give us similarly integral this double integral n x dx dy over d will give you n dy. Now, this we did for the very simple case of this region D. Now, if we have this kind of situation, we will see that here x is not changing. So, dx will be 0. So, it does not contribute anything to this, and therefore, there will not be any contribution on this curve here. So, one can extend this case to this more general situation, and supposing you have this kind of region here D, then what we will do, we will partition this into this kind of region here and do integration over each part. So, D is partitioned as d1, d2, d3 and d4 like this. So, here each one we will do integration, and these artificial boundaries introduced inside will the integration over them will cancel, like when we move like this on this d1, then on d2 we move this way, and we will go in the negative direction of this, and so the integration over this will cancel. Similarly, we go like this here, and when we integrate in this region, then we go in the negative direction of this, and therefore, the integration over these interior curves will get cancelled. So, here Green's theorem can be extended for more general situation like this. So, using this, we go back to the point here. We want to see that this integral I is actually giving you the area dx dy over the region D enclosed by this curve C here. So, that is what we can take the Green's theorem here, and so looking at this I, due to the lack of time we are not able to complete this concept here, which will be done in the next lecture. Thank you very much for viewing this lecture.